Hello and welcome back to Math Class in Session, Optimization Problems. Let's review our technique for using calculus to optimize things. The steps. In the last video, we minimized the tin necessary to make a cylindrical tin can. Example, a paper drinking cup in the shape of a cone has to hold 60 cc's of liquid. Determine the radius and height of the cup that minimizes the amount of paper needed to make the cone. Solution. Well, we're going to need a handful of formulas for this. Let's start with volume of a cone, which we know is going to be 60. And if we multiply by 3 and solve for h, we get this. Next, doing a little Pythagoras on the diagram. S squared equals h squared plus r squared. And solving for s. Next, our plan here is to get an expression for the thing we're trying to maximize or minimize. And we're trying to minimize the area. So we have an expression now for area. All we have to do is get it into just one variable. It looks like there's two variables there, r and s. That's why we did this work, so that we could take this s and plug it in right there. Let's do that. Great. Well, we're getting there. But we still have two variables because we have r and h. So we can take the h and use this. Now we have an expression in just one variable for the thing that we're trying to maximize or minimize. So all we have to do is prime it, zero it, and solve it. But as you can see, that may be easier said than done. But let's work on it. It's a project. Let's carry the project forward. And our goal here is to prime this and zero it and solve it. But first, we can process it a bit, simplify it. If we were to say square here, we have 180 squared, and on the bottom pi squared and r to the fourth. And then if we were to perform the operation of addition of fractions within this root sign, it will look like this with our common denominator. One needs to know how to add fractions. And now if we take the square root of the top over the square root of the bottom, the square root of the bottom is going to be pi r squared, which can come out here because we can take the square root of this denominator. And we'll leave the root sign for the numerator. This is fortunate because the pi's will cancel and the r's will reduce, leaving just that. Now it's looking more friendly, and maybe we can prime this. Let's try it. Using our quotient rule, it will be top thing prime times the bottom thing, minus the bottom thing prime times the top thing, over the bottom thing squared. So let's check it out then. dA by dr. Top thing primed. Well, within this term, we have 1/2 of 180 squared plus pi squared r to the 6th. 1/2 times 180 squared plus pi squared r to the 6th to the minus 1/2 times the derivative in here, which is going to be 6 pi squared r to the 5th. Here it is, 6 pi squared r to the 5th. Times the bottom thing, another r factor. So that makes that r to the 6th. So within this first term, we have the top thing primed, 1/2 of all of that to the minus 1/2 times 6 pi squared r to the 5th times r times the bottom thing. Minus the bottom thing primed, that's easy. It's just 1 times the top thing over the bottom thing squared. So you can see that it is now differentiated properly. All I did here was say 6 times a half is 3. And that's simplified a bit. Next, what happened here? Well, there's a negative exponent on this factor, so it's going to end up in the denominator under a root sign, like that. There it goes. But the thing is, that denominator is being shared with this term. So in putting it under there, I've also divided this term by the square root of 180 squared plus pi squared r to the 6th. So I must multiply this by square root 180 squared plus pi squared r to the 6th, so that undoes the effect of dividing it. Now that's a bit wordy. Maybe it's clear if you look at this. Just examine this statement. The q to the minus half goes downstairs under a root sign. But in so doing, it goes underneath this one as well. So this one has to be multiplied by root q as well, so that this is now still true. Consider q divided by its root is root q. Q divide out one of its roots, leaves its other root. So that's what's happening here. Take this, divide out this root, and you've got this, so that you know that it's right. Dwell on this a bit. Pause the video if you need to. At any rate, we now have the numerator set equal to 0, because we're going to prime it, zero it, and solve it. So we'll set the numerator equal to 0, because that's all that you need. The numerator must be 0. And you'll notice I subtracted here. So 3 pi squared r to the 6th minus makes it 2 pi squared r to the 6th minus 180 squared. Solving r to the 6th, taking the 6th, root both sides, and we have our radius for that cup. And that was quite a plate full of mathematics. Some meat and potatoes. Gee, I'm getting hungry here. So we've got r, we got our radius, and what are we going to do now? Well, we have this statement from before, h equals 180 over pi r squared, so we can simply sub it in and do the math on a calculator. And we have our height, the radius and the height of our cone. Let's do another example after this. How close does the curve y equals root x come to the point 2, 0? Solution, let q, x, root x, be the closest point on the curve, as shown. There's the point q, x, root x. There's our point p, 2, 0. And we can see the distance between them, d. So we have this formula, d squared equals y minus y squared plus x minus x squared. So root x minus 0 squared plus x minus 2 squared. Doing the math, taking the square root both sides and squaring out those brackets, we get root x squared is x, plus the square of a binomial, x squared minus 4x plus 4, all underneath that root sign. And simplifying, so we have an expression for d. And we want to minimize, so therefore we'll prime it, zero it, and solve it. 1/2 times the radicand to the negative 1/2 multiplied by the derivative of the radicand, 2x minus 3, and simplifying. And setting this equal to 0, we arrive at 2x minus 3 equals 0, just the numerator, and so x equals 3 over 2, or 1.5. Plugging this back into our expression for distance, we know that the minimum occurs when x equals 1.5. Just plug it in, evaluate it, and we have the shortest possible distance, 1.32 units.